In this lecture, we're going to continue solving inequalities, but now we're going to look at polynomial examples where the polynomial isn't linear, and we're also going to do some examples with rational expressions. The strategy that I'm going to push forward is a sign chart method. Basically, we're going to use a number line to display where the outputs of an expression are positive and where they're negative, and as long as you're comparing that expression with 0, then it's easy to determine where the inequality is true and where it's false. That's the basic idea. I've written out the process on this next slide. It's going to seem very abstract until we start doing examples. So if you don't get it from the first read through, don't worry about that. Hopefully it will make sense by the time we've done some examples in this video. Here's the basic process. We're going to get 0 on one side. As we discussed, that's going to be an important part of making this easier to do. So start by getting 0 on one side. Once you've done that, you're probably going to want to get the other side factored as much as possible. You're going to need to simplify, maybe collect some like terms, then factor. Once you've got it factored, you're going to draw a number line, and on that number line we're going to mark any inputs which yield 0 or any inputs that cause division by 0. These are the inputs that don't make the sign positive or negative, and we're going to divide the number line up based on those inputs. Then we're going to test an input on each of those intervals that we just created, determining whether the sign is positive or negative for those. And from there it will be easy. We're just going to select the intervals that satisfy the inequality. And talking about it without doing a specific example does not make this easy to understand. So we're going to do a bunch of examples in this video. And we're going to start with a couple where we don't have to worry about the first two steps. I know you're going to be able to get 0 on one side. I know you're going to be able to simplify and factor without much difficulty most of the time. It's the number line part that we need to focus on. So in our first example, we're asked to determine where the product of x minus 3 and x minus 5 is greater than 0. That is, where that product is positive. Before I show you the number line process, let me show you that the strategy that you would use for an equation would not work here. A common mistake is to write this as x minus 3 is greater than 0 or x minus 5 is greater than 0, because that's what you would do for an equation. This will not work here. There's actually two things wrong with this. In my opinion, the more obvious one is that this seems to indicate that these two numbers are both positive, that x minus 3 is positive and x minus 5 is positive. And yes, if they were both positive, then you would get a positive output. But it's also true that if they were both negative, you would get a positive output. And we've completely ignored that case here. That's a problem. The more subtle mistake here is that we've written or here where we really mean and. We need both of these to be positive. The strategy for solving equations does not work here. You can't split it up like that unless you're going to consider every possible case. The number line process is going to be easier. Making a sign chart will be more convenient. The first step is to get 0 on one side. That's already done here. The second step is to get the other expression factored. That's already done here too. So we can jump straight to drawing the number line. On that number line, we're going to mark any inputs that make the expression 0 or inputs that make the expression undefined. Now this is a polynomial, so it's defined everywhere. We don't have to worry about numbers that we're not allowed to plug in. That will happen with the rational expressions, but it doesn't happen here. But there are two numbers that will make this 0, and this is why we want this factored. It's going to be easy to determine what makes these factors 0. What makes the first factor equal to 0? Well, 3. So I'm going to mark that on the number line, and I'm going to put a little 0 above it to indicate that that made the output 0. Some people will skip that step of writing the 0 above it, but I'll show you examples where I think that step is important later. 5 will make the second factor equal to 0. Make sure you mark 5 somewhere to the right of 3. This is a number line, so you want everything in order. And again, I'm going to put a 0 above that. Now you can see we've divided the number line into 3 regions. There's the set of real numbers to the left of 3, there's the set of real numbers between 3 and 5, and the set of real numbers to the right of 5. We're going to select one representative, what we call a test point, on each of those intervals. You can pick any number that you want, but I would encourage you to pick something easy to work with. For example, to the left of 3, you could pick 2 or 1, but 0 is almost always easy to work with. So I'm going to select 0 as my test point. I'm going to plug 0 into each of these factors, and all I really care about is the sign. Is it positive or is it negative? This is the beauty of this process. The number itself doesn't matter. All that matters is the sign. So for this first example, I'm going to show you the thought process, but as we move on, I'm just going to write the signs. First, I plug 0 into the first factor, and I get 0 minus 3. That's negative. And so I'm going to indicate that with a little minus sign. I put that minus sign in parentheses because I'm going to be multiplying it by another sign here in a second. Then I plug 0 into the second factor. That also comes out negative. So I get a negative times a negative. Now you could actually do the math and figure out what the number is, but the number doesn't matter. All that matters is the sign. When you take a negative number times a negative number, that result will be positive. Go ahead and do the arithmetic here. You'll see that 0 minus 3 times 0 minus 5 is positive 15, and it comes out positive. But the 15-ness doesn't matter. All that matters is that it's positive. Now this following claim is what makes this process work. I claim that because the output at 0 was positive, the output at every input on that interval will also be positive. I claim that knowing that 0 gave us a positive output means that every input on this interval will also yield a positive output on the left side. The formal rule that we use to prove this doesn't occur until later on in the course, but hopefully I can appeal to your intuition. If this expression was to go from positive outputs to negative outputs somewhere along the line, then it would have to go through another spot where you get 0. But we've already found all of the numbers that give us 0, so there's no way that could happen. Therefore, these have to continue to be positive forever and ever. With rational expressions, you also have to worry about where it's undefined, but that's why we mark those spots. So every number on this interval gives you a positive output, and I'll show you how we use that information after we've completed the sign chart. Now we're going to plug in a number between 3 and 5, and you can pick any number that you want. You could pick 4 2/3, you could pick pi, 3.1415926535, blah, blah, blah. Again, I encourage you to pick something easy like 4. I'm going to plug 4 into the first factor. 4 minus 3 would be positive 1, but all that matters is that it's positive. 4 minus 5 would be negative 1, but all that matters is that it's negative. And if you can juggle that sign in your head, then that's what you should do. In future examples, I won't be writing this arithmetic underneath because all we care about is the sign. A positive times a negative is negative, and I claim that because the output of the left side is negative at 4, it will be negative for every number between 3 and 5. Again, I'll show you what we're going to do with that information after we've completed the sign chart. Now I can plug in a number bigger than 5, like 6. You might be obnoxious and pick something really, really big. Your test point should be something that's easy for you to work with. But 6 is easy to plug into both of these factors. 6 minus 3 would be positive, and 6 minus 5 would be positive, and a positive times a positive is positive. Now, what do we do with this information? Once you've made the sign chart, now what? What do you do? Well, remember what we were being asked to determine. We want to know where this product of x minus 3 and x minus 5 is greater than 0. Greater than 0 is what positive means. If a number is greater than 0, then it is positive. Well, we've just determined 2 intervals where this expression is positive. If you pick any input less than 3, this expression will be positive. If you pick any input greater than 5, this expression will be positive. So the solutions are the numbers on those 2 intervals. Either the number has to be on the interval from negative infinity to 3, not including 3, because at 3 the output was 0, but this wants to know where it's greater than 0. Or you need to pick an input bigger than 5, so on the interval from 5 to infinity, not including 5 for the same reason. Rather than writing or in between these, we usually use the union symbol. And our claim is that if you pick a number that's either less than 3 or greater than 5, it will make the inequality true. If you pick a number between 3 and 5, it will make the inequality false, and that's bared out by our sign chart. As long as our sign chart is right, you can see that that's absolutely the case. The sign chart is a nice way to organize your thoughts to figure out where the expression is positive and where it's negative. That hinges on you comparing with 0. If the right side was a 2, then this wouldn't be good enough. Just knowing that the expression is positive isn't good enough because we need it to be bigger than 2. Positive outputs like 1 or 3/2 would not satisfy the inequality. So it's important that you get 0 on one side when you're using this sign chart method. Let's do a couple more examples where we've already got a factored form and we can really just focus on making the sign chart. So in example 2, we're trying to determine where the product 10 minus x times x plus 20 times x minus 40 is less than or equal to 0. We've already got 0 on one side, we've already got it in factored form, we're ready to make the sign chart. Pause the video and see if you can find the 3 numbers that we're going to mark on the sign chart. And remember that this is a number line, so you have to put them in order from smallest to largest. Okay, the first factor is equal to 0 when x equals 10. The second factor is equal to 0 and x equals negative 20. So somewhere to the left of 10, I'm going to mark negative 20. And the third factor is equal to 0 and x equals 40. Now I know this is a number line, so we should have proportional spacing, but that's not the point of the sign chart. Just make sure you put all of the numbers in the correct relative position. Reading from left to right, the numbers should be getting bigger and bigger. You can see we've created 4 intervals here, and so we're going to need 4 test points. So right here I'm going to plug in negative 21. Now this time all I'm going to do is point at each factor and ask whether I get a positive or a negative result. The number itself doesn't matter. So when I plug negative 21 into the first factor, I get 10 minus negative 21. That is positive. When I plug negative 21 into the second factor, I get negative 21 plus 20. That's negative. And when I plug negative 21 into the last factor, I get negative 21 minus 40. That's also negative. A positive times a negative would be positive. The shortcut rule is if you have an even number of negatives, the result will be positive. Looking ahead to the end of the problem, you can see that we're interested in where this expression is less than or equal to 0, so we will not be including the numbers to the left of negative 20 because they gave us positive results. Between negative 20 and positive 10, there are lots of good choices, but I'm going to pick 0. Anytime 0 is an option, I like to use it. 0 is almost always easy to plug in. So 10 minus 0 is positive. 0 plus 20 is positive. 0 minus 40 is negative. And a positive times a negative, that would be negative. The numbers on that interval will be solutions because we want to know where this output is negative, where it's less than 0. Between 10 and 40, I could pick 20. I could also pick 30, or I could pick 32. There are lots of numbers you could pick, but I would just pick something easy to work with. 10 minus 20 would be negative. 20 plus 20 would be positive. 20 minus 40 would be negative. That's an even number of negatives, so this product is positive. And on the last interval, I would pick 50. You could also pick 41, or you could pick 100. 10 minus 50 would be negative. 50 plus 20 would be positive. 50 minus 40 would be positive. That's only one negative. This product is negative. There are 2 things that are different about this example compared to the previous example. In the previous example, we wanted to know where the output was greater than 0, so we were looking for the plus signs. In this example, we want to know where the output is less than or equal to 0. So we're looking for the minus signs because that indicates that the output is negative. But we also want to include the bounds this time because those bounds satisfy the inequality too. That makes the output equal to 0. So the first stretch of negatives ranges from negative 20 to 10. But I'm going to use brackets on both of those because both of those inputs give us a solution to the inequality. They both make the output equal to 0. There's a second interval of minus signs that ranges from 40 to infinity. 40 would get a bracket because it makes the output 0. Infinity is not something you're plugging in and getting a result to. It's a way of expressing that there's no upper bound on this interval. So you don't put a bracket on that, you put a parenthesis. That might not look like a parenthesis to you. Let me rewrite that. There we go. And then the union symbol to indicate that the solutions live on both. That either the number could be between negative 20 and 10 inclusive, or it could be on the interval from 40 to infinity, including 40. Now at this point, a lot of students notice that the signs seem to alternate. In these 2 examples, they did. In the first sign chart, it went plus, minus, plus. In the second chart, it went plus, minus, plus, minus. I want to warn you that the signs do not always alternate. When we've learned a little more algebra, there's kind of a shortcut way to determine when they'll alternate and when they won't. But we're not ready for that yet, so we're going to have to make the entire chart. But here's an example where we're not going to get alternating signs all the way across. This one says, determine where negative 5 times the square of x minus 4 times x plus 7 is strictly less than 0. We already have 0 on one side. The left side's already factored. We're going to make a sign chart. The outer factor is never equal to 0 because it doesn't have an x in it. What are the inputs that will make this equal to 0? Mark them on your number line. 4 will make this 0. Negative 7 will make this 0. Negative 5 doesn't make the expression equal to 0. Don't list that one. However, when we were determining the sign of the output, that negative 5 is going to have something to say. That factor is always negative. You'll see me indicate that as we go through our sign chart. To the left of negative 7, I could pick negative 8. Negative 5 is always negative. That first factor is always negative. X minus 4 squared is going to be positive as long as the input isn't 4. When you plug a number in here, you're going to subtract 4, but then you're going to square the result, and we know that the square is always going to be non-negative. So we're going to get a positive result from that squared term. Negative 8 plus 7 is negative, and so we get a negative times a negative, that's positive. So this product is positive. Between negative 7 and 4, I'm going to pick 0. Negative 5 is always negative. X minus 4 squared is going to be positive at x equals 0. It's going to be positive everywhere except at 4. 0 plus 7 is positive. That's a negative times a positive, that's negative. Pick a number bigger than 4, I would pick 5. Negative 5 is always negative. 5 minus 4 squared will be positive. 5 plus 7 squared is positive. And again, you see we get a negative times a positive. The signs did not change. And just as a preview of what we're going to learn in the future, it's because of that square that the signs didn't change. Because x minus 4 squared will never be negative, the signs don't alternate all the way through. It's not coincidence that the place where the signs failed to change was at the very number that made this 0. We're being asked to determine where this product is strictly less than 0. So that's the interval from negative 7 to 4, as well as the interval from 4 to infinity. We cannot write this as a single interval, because at 4 the output is 0 and we don't want to include that. So our solution is going to be the union of the interval from negative 7 to 4 and the interval from 4 to infinity. This is the interval notation way of saying all of the numbers greater than negative 7 except for 4. We skipped over 4 by making it the upper bound of this interval and the lower bound of the second interval and putting parentheses on each. That excludes it from the solution. Again, there's an example that shows you that the signs don't always alternate, so you can't count on that. All right, let's look at an example where we have to do a little bit more work. In this problem, we're asked to determine where x squared plus 2x is less than or equal to 63. A sign chart won't work as it's written. Factoring the left side won't work because comparing with 63 won't be that easy to do. It's much easier to compare with 0. So we're going to start by getting 0 on one side. We're going to subtract 63 from both sides, and we get x squared plus 2x minus 63 is less than or equal to 0. Comparing with 0 is nice because now all we have to worry about is where the expression is positive and where it's negative. With a little bit of guessing, you could figure out where the expression on the left is positive or negative without factoring, but factoring is going to make it so much easier. See if you can get this expression factored. Okay, so we're looking for two numbers that multiply to negative 63 and add to positive 2. Hopefully came up with positive 9 and negative 7. And now that we have it factored, it's easy to determine where this expression is positive or negative. We organize this with a sign chart. The number that makes the first factor equal to 0 is negative 9. The number that makes the second factor equal to 0 is 7. Make sure you put that somewhere to the right of negative 9. And now I just pick test points. I want you to try to do this one on your own. Pick a test point for each of the 3 intervals and see if you can come up with the signs. All right, to the left of negative 9, I would pick negative 10. Negative 10 plus 9 is negative. Negative 10 minus 7 is negative. A negative times a negative is positive. And therefore the expression is going to be positive for all inputs less than negative 9. Between negative 9 and 7 lives 0. 0 plus 9 is positive, but 0 minus 7 is negative. A positive times a negative is negative. Note that this is an interval we're interested in because we want to know where the expression is less than or equal to 0. If you pick a number bigger than 7, like say 8, 8 plus 9 is positive, 8 minus 7 is also positive. A positive times a positive is positive, and we don't care about those. So the only interval we care about is the interval from negative 9 to 7, inclusive, because of the or equal to. We want to include the bounds because the bounds give us outputs of 0, and we want to know where the output of this is 0. So our solution set is a single interval this time. It just ranges from negative 9 to 7 inclusive. The only way to make these problems any harder is to make the factoring more difficult. So here's an example with that. This asks us to determine where 4x cubed minus 8x squared minus 9x plus 18 is greater than or equal to 0. And so we're stuck having to factor a 4-term polynomial. I've encouraged you to try factor by grouping first, and factor by grouping doesn't always work, but it's the first thing to try. When factor by grouping fails, there's a technique we'll learn later on in the course, and if that didn't work, then we'd be stuck. We wouldn't be able to do it. Let's see if we can factor this one by grouping. The GCF of the first two terms is 4x squared, leaving behind an x minus 2. And for the last two terms, we can pull out a 9, but pulling a positive 9 out won't make the binomials match. We need to pull out a negative 9. Pulling a negative 9 from the first term leaves behind an x, and pulling a negative 9 from a positive 18 leaves behind a minus 2. And that's important because these two binomials have to match. If you're trying to factor a 4-term polynomial by grouping, and the binomials you get don't match, then your attempt has failed and you have to try something else. But we're good here. I pull out the common factor of x minus 2, leaving behind a 4x squared minus 9. And now we want to get this factored even further because it will be easier to determine where the expression is positive or negative by having it completely factored. That is a difference of squares on the right there. It factors to 2x plus 3 times 2x minus 3. Okay. Let's draw our number line. I want you to mark the numbers that make this expression equal to 0. Make sure you get them in order. The first factor is going to be equal to 0 when x equals 2. The second factor is going to be equal to 0 when x equals negative 3/2 or negative 1.5. It doesn't matter to me whether you use the decimal or the fraction here because the decimal expression terminates. But in general, it's safer to use the fractions. The third factor is equal to 0 when x equals 3/2. Put my zeros on top here. Now we pick our test points, and I'm going to walk you through the test points here just because one of these test points is a little more difficult than what we've seen in the past. The first one's not that bad. Negative 3/2 is bigger than negative 2, so I can use negative 2 as my test point. Negative 2 minus 2 is negative. 2 times negative 2 is negative 4, plus 3 would be negative. Negative 2 times 2 would be negative, minus 3 would be negative. That's the product of three negatives, and so this starts off negative. This is actually the first example we've had that started off negative. You should know that that can happen. I know every other example has started off with plus signs, but that doesn't have to happen. Between negative 3/2 and 3/2 lives 0. 0 minus 2 is negative. 0 plus 3 is positive. 0 minus 3 is negative. That's got two negatives, so the result would be positive. Again, that's the shortcut. Just count how many negatives there are. There were 3 negatives here, so the result is negative, because a negative times a negative times a negative will be negative. This one only has 2 negatives, and so the result will be positive. Here's the one that's a little bit of a pain. 3/2 is 1.5, and then the next number is 2, and there aren't any integers between those, so we're going to have to use a fraction or a decimal. Now, I know I said I would use fractions here, but for my inputs, I would use a decimal. The reason why I'm telling you to use a fraction here is that sometimes you're going to get fractions like 2/3, and that doesn't have a terminating decimal, so you have to use the fraction in your representation. But for plugging in numbers, I find it easier to use decimals. So between 1.5 and 2 lives a number like 1.9. 1.9 minus 2 is negative. Even if you can't do 2 times 1.9 in your head, you know that that's a positive times a positive, and then you're going to add 3, that's still positive. The actual number is going to be 3.8 plus 3, which is definitely positive. Over here, we're forced to do the decimal arithmetic because it matters how big this product is before we subtract 3. But again, 2 times 1.9 is 3.8, and 3.8 minus 3 is positive. So we only get one negative factor out of that, and that string is negative. For representative bigger than 2, I would pick 3. 3 minus 2 is positive. 2 times 3 plus 3 is positive. 2 times 3 is 6, and 6 minus 3 is positive. That's the product of 3 positive factors, which is definitely positive. Now all we have to do is pick off the regions that we want. See if you can write the final answer. Be careful about the grouping symbols that you choose. All right, first, which strings do we want? Do we want the pluses or the minuses? Well, we're asked to determine where this product is greater than or equal to 0. So we want the strings of pluses. There's one string of pluses that ranges from negative 3/2 to positive 3/2. And what are the correct grouping symbols on that interval? Well, we want to know where this product is greater than or equal to 0. And at negative 3/2, the product is 0, so we want to include that. At positive 3/2, the product is 0, we want to include that. The other interval that includes pluses starts at 2, including 2, and extends infinitely to the right, so to positive infinity. We can take answers on either, so we want the union of these two for our answer. I know it's kind of annoying that we did all of the hassle of plugging in the 1.9 and then it wound up not even being part of our solution. But unless you know some of that stuff that we're going to learn later in the class, that would be hard to determine, so we have to test the point. Okay, I think we're good on polynomial examples. Let's look at a couple of examples with rational expressions. We'll start with the most basic type. Here we've already got 0 on one side and nothing factors here. Please don't cancel these x's. I know you're tempted to cancel these x's, but you can't just cross out things that match. I know both of these are divisible by 2, but you can't cancel those either. You don't get to cross out things that match. You can only cancel common factors, and we can't factor anything out of these. Canceling a 2 from each of those factors would be equivalent to canceling this x with this x. If you think that's ridiculous, that's what I think when you cancel a 2 from both of these. You're not allowed to cancel things unless they are common factors, and we can't factor out a 2, and we can't factor out an x, so we cannot cancel here. But that's okay, we can just run with the expression as it is. Since nothing factors and we're already comparing with 0, we can just jump straight to our number line. Now what makes the numerator equal to 0? Well, negative 10. And when the numerator of a fraction is equal to 0, the fraction is actually equal to 0. It's okay for the top of a fraction to be 0. What would make the denominator 0? Positive 4, right? But positive 4 causes division by 0. So I'm not going to mark this with a 0, I'm going to mark it with a U for undefined. Now, if you don't want to do that, that's fine, but I need that reminder when I do these problems. I need to know that 4 is not an allowable input. You'll see why that's important in the next example. It won't really matter here, but it will matter in the next example, so I stay in that habit. The beautiful thing about working with rational expressions is that we're going to use the same rules we used before because the sign rules for division and multiplication are the same. For example, a negative divided by a negative is positive, just like a negative times a negative is positive. All of those sign rules are the same. So our logic is the same. I'm just going to draw my work a little bit differently. I'm going to pick a test point on the first interval. Let me select negative 11. I'm going to plug that into the numerator. Negative 11 plus 10 is negative. I'm going to put that on top of a fraction. Then I'm going to plug negative 11 into the denominator. Negative 11 minus 4 is also negative. It doesn't matter what the numbers are because all we care about is the sign. That's the nice thing about comparing with 0. A negative divided by a negative is positive, just like we said before. And there's no way the sign can change to the left of negative 10 because we've already found all of the zeros of the top and the bottom. We found all of the inputs that make the top and the bottom 0. So there will be no sign changes to the left of negative 10. Any number less than negative 10 will make that quotient positive. Between negative 10 and 4, I would pick 0. The numerator will be 0 plus 10, that's positive. The denominator will be 0 minus 4, that's negative. And a positive divided by a negative is negative, and so I claim this entire stretch will be negative. That's a stretch we're going to care about, right? Because we're being asked where this quotient is negative. Now I pick a number bigger than 4, like 5. 5 plus 10 is positive. 5 minus 4 is positive. The quotient of two positives is positive. And we don't really need that stretch anyway. What numbers do we need? We need the stretch of numbers from negative 10 to 4. We're not going to include negative 10 because we're asked where this is strictly less than 0. So negative 10 is getting a parenthesis. And 4 gets a parenthesis because it's not an allowable input. You might have lucked into that because of the less than. You may have built up this rule in your head that the strict inequalities always use parentheses and that would work. And you'd get away with that here. But if you're thinking the other way, that less than or equal to and greater than or equal to will always give you brackets, well, be careful about that. Here's an example. This says x minus 1 divided by the trinomial x squared plus 5x plus 4 is greater than or equal to 0. I don't want to make the number line yet because the denominator isn't factored. See if you can get that factored. It factors to x plus 1, x plus 4. Now we're going to make a sign chart. I want you to determine all of the numbers that make the factors in the numerator and denominator 0. Those three numbers are negative 4, that comes from this factor, negative 1, that comes from the other factor in the denominator, and positive 1. And the way that I would mark these is as follows. Positive 1 made the numerator 0, so I'm going to mark that with a 0. -4 and -1 make the denominator 0, which causes division by 0. So the expression is undefined, and that's going to matter in this example because of the type of inequality we're looking at. Now it's time to pick test points. Pause the video and see if you can come up with the signs. My test point of -5 made all of the factors negative. That's an odd number of negatives, so the result is negative. A test point of -2 only makes the second factor in the denominator positive. That's an even number of negatives, so the result is positive. My favorite input 0 makes the numerator negative, but both factors in the denominator positive, so that quotient would be negative. And 2, or anything bigger than 1, will make all of the factors positive, and so that quotient's positive. Now, which inputs are we interested in? We want the ones that make the output greater than or equal to 0. So we have the stretch from -4 to -1, where we have plus signs, that's greater than 0. And in previous examples, when we've had an or equal to, we've included the bounds. But you would not include these bounds because they make the denominator 0. And that's why I write these u's. These u's remind me that, hey, the output there isn't 0. There's no output at all. The expression is undefined. So I would not include either of those. When I look at the second stretch of plus signs, it starts at 1. And I would include 1 because that's what makes the numerator 0, and that was indicated with the 0 on top. This extends forever to the right, and of course infinity always gets a parenthesis because we're not using it as a number. Take the union of those two as our solution. That's why I write the u's and the zeros. It helps me remember which inputs give me a 0 and which inputs made the expression undefined. You don't have to do that. If you've taken the time to factor everything, then you can just see it by looking back at the expression. But I'm in the habit of writing those down most of the time. Of course, sometimes I forget, especially when I'm doing problems for myself. When I'm demonstrating this for people who've never seen it before, I try really hard to remember to put those in there. I think they're useful. One more rational expression, and then we're going to do a bonus polynomial example. We haven't done a rational expression example where we didn't have 0 on one side already. So here's an example of that. We have x minus 2 over 3x plus 5 is less than or equal to 4. Making a sign chart right now won't work because if we determine a stretch is positive, we don't know if that positive number is bigger than 4 or less than 4. You have to get 0 on one side for the sign charts to work. So I'm going to subtract 4 from both sides, and I get x minus 2 over 3x plus 5 minus 4 is less than or equal to 0. A sign chart won't really work here either because I don't have this written as a quotient. I have this written as a difference. So I'm going to get a common denominator. And the easiest way to do that is to multiply by 3x plus 5 over 3x plus 5 in the second term. So I can combine this into a single expression because I have a common denominator. And I can distribute this -4 through here. This is -12x minus 20. And collecting the like terms, I get -11x minus 22 all over 3x plus 5. Let me take this to the next slide. You can pull a -11 out of the numerator. And so we've got -11 times x plus 2, all divided by 3x plus 5. We want to know where that's less than or equal to 0. Let's make our sign chart. This one's got a little more bite to it, so I'm going to walk you through it. The numerator is equal to 0 and x equals -2. -11 doesn't make this equal to 0. That's just a factor on the outside. The denominator is equal to 0 at -5/3, which is just a little bit bigger than -2. It's like -1.6666666. Test point to the left of -2, well, I would pick -3. -11 is always a negative factor. -3 plus 2 is negative. 3 times -3 plus 5 would also be negative. So I get a negative times a negative divided by a negative, that would be negative. Here's another one of those pains. -2 and -5/3 don't have any integers in between them. So I'm going to pick some decimal in between them, like -1.75. You have some other options in here. There's nothing really nice that you can plug in there. The -11 is always negative. -1.75 plus 2 will be positive because 2 is bigger than 1.75. In the denominator, 3 times -1.75 is -5.25. And since 5.25 is bigger than 5, that will be a negative result. So we've got two negatives here. That will be a positive quotient. Thirds, we've got good old 0. So the first factor is always negative. 0 plus 2 is positive. 0 plus 5 is positive. We've got a negative divided by a positive, that's negative. See if you can write the interval notation. Aha, I hope you noticed that I didn't write in the 0 and the u, and I did that on purpose because if you weren't paying attention to that, then you may have written the solution incorrectly. At -2, the output is 0 because it makes the numerator 0, but at -5/3, the expression is undefined. It matters here. This is why I do this. We want to know where this expression is less than or equal to 0. The first stretch has no lower bound and goes up to and including -2 because -2 makes the output 0. Then we've got the stretch of positives that we can ignore because we want to know where this is less than or equal to 0. The second stretch starts at -5/3, but we can't include -5/3 because it makes the denominator 0. It has no upper bound. It goes on forever and ever. And so we take the union of those two. Determining where the expression is equal to 0 and where it's undefined matters because in these kinds of problems you have to worry about excluding the numbers that make the denominator 0. That's why I put those in there. Consider this last example a bonus problem. A lot of textbooks have problems like this, and so I want to demonstrate this one time. This is a polynomial example. This says x to the fourth is greater than or equal to x squared. A lot of people have a knee-jerk reaction and assume that x to the fourth is always greater than or equal to x squared, but that's not true. First thing we want to do is get 0 on one side, so we subtract x squared from both sides. X to the fourth minus x squared is greater than or equal to 0. Then we factor, we get x squared times x squared minus 1. Don't forget the minus 1 in the back. When you factor an x squared from a binomial, it should leave behind a binomial. A common mistake is to forget that minus 1 in the back because they say that this completely went away. But there has to be something there for the x squared to distribute to. It has to distribute to a -1 in order to get a minus x squared. X squared minus 1 is a difference of squares, so it factors to x plus 1, x minus 1. 0 makes the outer factor equal to 0. -1 makes the second factor equal to 0. Positive 1 makes the third factor equal to 0. And we've got all of our intervals defined. Now we pick test points. X squared is always going to be positive except at x equals 0. So that first factor is going to be positive for all of our test points. -2 plus 1 is negative. -2 minus 1 is negative. A positive times a negative would be positive. This starts off positive. Here's another one of those situations where we can't pick an integer, but this one's not as bad. Between -1 and 0 leaves -0.5, -1/2. -1/2 squared will be positive. -1/2 plus 1 will be positive, but -1/2 minus 1 will be negative. That stretch is negative. In between 0 and positive 1 is positive 0.5. Positive 0.5 squared will be positive. Positive 0.5 plus 1 will be positive. Positive 0.5 minus 1 will be negative. And we get another example where the intervals don't alternate. Make sure you're not assuming that that happens. To the right of 2, every factor will be positive, and so the result will be positive. Okay, so we have to look for the plus signs and where this thing's equal to 0. And this is why I wanted to do this example, because this has something that doesn't come up very often. There's a stretch of numbers to the left of -1 where we get plus signs, and there's a stretch of numbers to the right of positive 1 that we get plus signs. And of course we want to include those two bounds because we want to know where this is equal. The weird thing is that at 0, the output is 0. So 0 satisfies the inequality, but the numbers around it do not. So we can't use interval notation to include the 0 because there's no interval there. So how do we handle that? We use set braces for that part. So let me go from left to right. The first interval has no lower bound, goes up to and including -1. The next part I want to include is just 0. It's not an interval. So to indicate that a singleton 0 is also a solution, we write 0 inside those curly set braces, which you can see I can't draw very well. We can't use interval notation for that solution because it doesn't sit on an interval. We can't take the interval surrounding it because all of the outputs around it are negative. So we just include this singleton like that. The last interval starts at 1 including 1 and goes forever and ever to the right. There are a couple examples like this in most textbooks, so just in case you run across that in your practice, I wanted to make sure I'd shown you one of those. Now, I'm personally not the kind of monster who would ask an example like this on a quiz or exam unless my students had really irritated me and I was out for vengeance. I would be more focused on examples like, say, this one, where you have to do a little bit of work in order to get it factored, or maybe this one. And I like these examples because they're similar to what future calculus students will see. You spend some time in calculus determining where derivatives are positive and where they're negative. That has a meaning. And so being able to do this is going to be important for those students. It comes up in other applications as well, but that's the first thing that comes to mind. If you need any help, reach out to me.